Drop past 200 meters and the sunlight fades completely. This is the deep sea, an environment making up roughly 95% of Earth's ocean volume. Down here, the temperature hovers near freezing, and the darkness is absolute. Then there is the physical pressure. For every 10 meters you descend, the weight of the water increases by 1 atmosphere. By the time you reach the abyssal zones, the force pressing in on every square centimeter of space is equivalent to the weight of 4 sumo wrestlers standing on your pinky nail. Standard biological logic suggests that in a habitat with 0 sunlight and almost 0 food, animals must stay small to survive. Tiny bodies require minimal calories, making them highly efficient when resources are practically non-existent. Yet this starved, high-pressure environment produces massive biological outliers. Take the giant isopod. A typical crustacean should be a fraction of this size, but this deep-sea scavenger grows to nearly half a meter long. The Japanese spider crab is even more extreme, dragging a leg span of 3 to 4 meters across the ocean floor. And elsewhere in the dark, the giant oarfish can stretch up to 20 meters long. This creates a direct contradiction. Why does the most resource-starved environment on Earth produce its largest creatures? One explanation involves how these animals manage their internal clocks. In freezing water with scarce food, deep-sea creatures drop their metabolic rates to an absolute crawl, processing energy at a fraction of the speed of surface animals. This extreme pacing allows them to endure massive gaps between meals. One captive giant isopod actually survived in an aquarium for 5 full years without eating a single bite of food. The Greenland shark takes this biological stretch even further. It moves at roughly 1 kilometer an hour, growing just 1 centimeter per year. Because it burns energy so slowly, it can live for up to 500 years. When you live for centuries in the deep with almost no natural predators, you simply never stop growing. Mass is accumulated not through abundance, but through time. Bergmann's rule dictates animals in colder climates evolve larger bodies to retain heat. This massive volume-to-surface area ratio also solves oxygen scarcity, allowing creatures to develop the massive gills necessary to extract the abyss's scarce oxygen. For these animals, becoming huge is a physical byproduct of adapting to survive starvation. But surviving starvation and freezing temperatures means nothing if the ocean crushes you first. How do these massive bodies withstand 1,000 atmospheres of pressure? The first step is removing structural weaknesses. Most shallow water fish rely on air-filled swim bladders to stay buoyant, but air collapses easily under force. Deep-sea fish replace these air pockets with fats and waxes, liquids that do not compress. The real defense happens cellularly. Extreme pressure deforms proteins, but deep-sea tissues are saturated with TMAO, molecules acting as microscopic scaffolding to prevent structural collapse. As this chart shows, there is a strict correlation. The deeper a fish lives, the more TMAO armor it requires. Deep-sea gigantism is physically possible because these creatures have evolved microscopic bracing that functions under forces that would flatten a human submarine. Even with these thermodynamic and chemical explanations, the biological record remains inconsistent. We still don't know why only specific creatures experience this gigantism, while millions of other species in the exact same environment stay incredibly small. This gap in our understanding comes down to access. Humans have mapped less than 30. To put that ignorance into perspective, researchers surveying below 2,000 meters in 2022 discovered a brand new species of slickhead fish called the Yokozuna iwashi. It was a massive 2-meter-long apex predator. Finding an apex predator of that size this recently highlights the limits of our sensors. It suggests the abyss is still hiding massive populations just beyond the reach of our submersible lights. The deep sea is Earth's final alien frontier, an expansive, pitch-black laboratory where life expands the known limits of size and chemistry to survive the absolute extremes of our planet.